Everyone see?
Sorry.
Look good on the camera?
Yep.
Okay, good. To welcome World and Juniors, it's Thursday. And we are back to graph theory. Yesterday we took a Polyhedra detour. We're going to go back to that as well today after we finish going over this homework. On Tuesday, we discussed the four-color theorem. What should I be like in front of this camera while talking?
I'm going to be standing up for this, but I'm good.
Cool. Good, let's do this. On Tuesday, we discussed the four-color theorem. What's the four-color theorem? It says that if you have a map, you can color the regions of the map with just four colors. And that makes all kinds of assumptions about the way they meet and blah, 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 blah. How did we choose to attack this problem? We said, well, we can put a point at the center of each region and we can connect two regions with an edge if and only if they have a border in common. Yeah? Yep. And that led to the concept of the dual of a graph. And one colors, if you can color a map, if the dual can be colored in such a way that no two vertices have the same color. Cool? Alright, then there was a homework assignment that was briefish, I don't know, on the order of 25 minutes maybe, on dual graphs and graph colorings. Being honest, how many of you did it?
I didn't do all of it.
One person. Good.
I did all of it. I did like half.
Good. Alright.
I did all of the Polyhedra ones.
Good.
Because
that's kind of fun.
That was more interesting.
Yeah, that
the
was
other one I just got bored.
good. Alright. Alright, so here, can you zoom in ish on this icosahedral graph? This is the stereographic projection of the icosahedron. Just make sure it's in frame of that. And what I would like to know is, what is chi for this graph? Chi is the minimum number of colors required to color every vertex of this graph in such a way that no two adjacent vertices have the same color.
You can, oh yeah, you got it.
One person who did their homework. Jason, talk to me. What'd you get? What's your answer?
4.
He got 4. Shall we just do this problem together right now as a class?
Sure.
Okay, good. Are you impressed that I prepared this document?
Yes. It's actually, yeah.
All right.
Actually, yes, I am impressed.
Good. Shall we? What's your favorite color, Ryan Holland?
My favorite color.
Red. Good.
Red.
Okay, so suppose I color this vertex red. Talk to me. I want to hear your thoughts. Maggie, give me a thought. Oh, good. It's taking too long. You guys are not jumping in to participate in the way I was
The ones
hoping.
that touch it can't be red.
The ones that are adjacent to it can be red. Good. That was a contribution. Good. So I have.
Are we coloring the?
Is that green or just green?
So as I said in my rambling warm-up, ultimately we are interested in coloring regions. But every problem about how to color regions can be converted into a discrete problem by putting a vertex at the center of every region. No, we are just now pretending that it's already been done. So the interesting problem is, how do I color the vertices of a graph in such a way?
I thought we were planning coloring.
Is the dual?
Because we were once interested in coloring regions, we have decided that we're interested in coloring graphs, because by taking the dual of any bunch of regions. Do I need to say more about this, or?
No, wait. I just thought that.
All right, we're coloring vertices. That's what we're doing.
Is the dual of a stereographic projection of a polyhedron like the stereographic projection of its dual?
Probably not.
guess.
Maybe yes. Just do it for the octahedron and the square. Good. Meanwhile, wait. This is taking too long. We're supposed to spend 1 minute each on these. Give me a contribution. Read. Say something.
Yeah, that one.
This one?
Make that one green.
This one can be green or blue. That's a fact. Yeah.
Yeah.
Can be, right?
Okay. So let's make it. What do you want to make it?
Let's make it green.
Let's make it green. Woo! What can this be? Uh-oh. Can this be green?
No.
Can it be red?
No.
Can it be blue?
No.
No. So look, as I have arbitrarily picked 3 different colors for the 3 outside vertices, and if I was forced to assign a color to this top vertex, I chose arbitrarily one of blue or green because it can't be red. You see what I'm doing here? I'm attempting to color it with just 3 vertices. And as this graph is completely symmetrical, the degree of every vertex is 5 and they're all exactly connected in the same kind of way, I claim that it's got to be at least 4 now, right? Because there's no way I can't color this red, green, or blue. So let's color it like yellow. Now so therefore chi for this graph is at least 4. I want to show that chi is exactly 4. For that, I need to produce the coloring. So can I do this in 4 colors?
Yes.
Hopefully, yes. What should I make this?
Yellow.
It could be yellow or blue, but someone has wisely said, let's make it yellow. What'd you get over there, Elijah?
I tried it with a cube. I didn't get the stereographic projection of an octahedron, but I got something that's isomorphic.
Good. Moving on. Now what should I do? Someone finish this off. Tell me what to do. You're supposed to be doing the homework
Red.
now, if not at home.
Red.
Jason.
Red.
Red. Woo! Excellent video we're making here. What can this be?
Blue.
Yeah, all right. Now the class is on fire. What can this be?
Green.
Or yellow.
Or yellow.
Or yellow.
Or yellow.
It should be yellow.
It should be
I
yellow.
think we
It should be
need to
yellow.
make it yellow because I need
Yeah.
this to be green. Yeah.
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 Green.
Oh, this is riveting. We getting all this on video?
Oh
What
yeah.
should this be?
Red.
It has to be red. Then this would be green.
No.
No?
Oh yeah.
No,
Oh.
we're good. Blue.
No.
We win.
No.
No. Wait, it has to be blue. It has to be blue. And then that bottom one
What could-
has
No,
to be.
we
Damn.
messed up.
No, it has to be
Goodness,
blue.
that
Maybe switch like the
Yeah,
red
the 2 bottom
one.
ones. Which 2? These 2?
No, no, no,
These
oh,
2.
I guess that works too.
Oh no.
Oh, so make this
Other
red
one.
and this
No,
blue.
that has to be.
No, he's right.
Yeah,
Right.
just
that
switch
works.
those 2. Just switch those 2 and you get
He is so right. Red
No, blue.
and
There you
blue. Woo! All right. Good job, us. Icosahedral graph has a chi of 4. All right, good. Do you see how? Oh, this was the answer. This was an answer. Good. Next, the Haywood graph, as it is called. And the Haywood graph, by the way, you might be interested to know, is the graph is not planar, but it's planar on a torus. And in fact, the Haywood graph is precisely the graph of the vertices of the Székely polyhedron, which is just an insane freaking polyhedron, man, which is composed of topologically a torus, Euler characteristic 0, composed of 7 polygons, polygonal faces. Each polygonal face is a hexagon, an irregular hexagon, including this little weird hexagon in the middle here. Every face of the Székely polyhedron shares an edge with every other face. The only other polyhedron with that property is the tetrahedron. It's crazy.
Is that a toroid?
That is a toroid. You are correct. Good. So, how can we color the Haywood graph?
Just like do it.
Just do it.
Red.
Let's use pink this time.
All right. Color pink.
Yeah.
Not pink.
Not pink.
Just pink.
Pink.
What is anyone noticing anything? Note what let's call this the left, right, and then let's call this left, right, etc. It's almost kind of a cycle, but then the left one is always connected to the right one. Someone say something smart. Just alternate. Can I hear some like vocab?
Bipartite.
It is bipartite. Thank you. Good. It just straight up just is freaking bipartite, man. That's a fact. Is that obvious? No. Was it obvious to Dilhan? Yes. Boom. Done. That is a coloration. Does it work?
Yeah.
Yeah, it does, because the Haywood graph is bipartite. Crazy. Is there anything deep to say about that?
Well, it's wild to think about that, like polyhedra is incredible.
It is kind of wild. That's what I was trying to process myself. Like, I don't know how. I don't even know what the hell's going on, frankly. 1, 2, 3, 4, 5, 6. Yeah. Good. All right. Next. We don't need to do all of these necessarily, but we should do a couple. This is the Walter graph,
How are these named?
named after people.
Sure, but like, is it just like the person who first drew the graph or something?
Pretty much, yeah.
So I should just draw something, check to make sure nobody else is drawing.
Well, I
or
think
it's
you're,
like-
the
this is
thing you
nice.
It's gotta have
draw,
some interesting
it's got to have
properties.
some interesting property. The Walter graph, we looked it up today during 5th period, is a graph such that if you do like 3 of them together, it's like the Tuta graph or some crap like that, which is a graph which is famous because it's like a counterexample to some conjecture. Someone back me up on that via
Yeah.
Yes,
our
yeah, exactly.
Wikipedia.
Yeah.
Or I could just back it with the power.
Everyone's backing me up. All right, good. How do we color this little boy?
Just like big one.
Well, so wait, you can start on like you can ignore those like end ones because they can just be whatever.
Yeah, I like it. I like it.
So start with one of like.
Is this graph bipartite? No. Yes. No.
No.
No. Yes.
Is there cutting that? If it's two, it's bipartite.
I think so.
Yeah. Yeah, it's bipartite.
Oh boy.
It's bipartite.
Woo!
Wild. It can't be. I almost don't
No,
believe
no,
it.
no.
It's bipartite.
Oh wait, it's
It's
not.
bipartite.
Wait, no, it is.
Definitely
It's
is.
bipartite.
Definitely
It's
is.
just hit every other one.
Yeah.
Yeah, and then get that middle one.
Yeah. Oh yeah.
Wow.
Favorite color? Orange?
Yes.
Yes.
Halloween theme?
Great.
Woo! That's a glorious coloration. Kai, 2. Alright, this, you guys laughed at me yesterday when I called this the alien spaceship graph.
But when I
But it's
Google
actually what
alien
it's called.
spaceship graph, it's not. I think it's just what he calls it.
Gossip, just put it in quotes, it's true.
Yeah.
Yeah, good. Well, I'm
Gossip.
calling it the alien spaceship
Gossip, that's
graph.
Gossip's name.
I don't feel like doing this because this is kind of starting to become like annoying. But anyway, does everyone get the idea?
Yes.
Okay, good. Let's get to some real problems now. Moving on to number 10. What is the chromatic number of the cycle graph? Well, it depends whether odd or even. If it's even, then what can I say about the cycle graph if it's even? The chromatic number is just 2. Okay, what can I say about the cycle graph if it's odd? It's gotta be 3. You are so right. Because like you can make these like red or whatever, and you can make these blue. Everyone calling this? Yeah, but then like, nah man, I need another color for that. Alright, good. How about this thingy over here? How about this one? Let's do this one first, the wheel graph.
3.
Now I think it's just like 3, right? Because these two can be red, those two can be black, but then this one needs to be like something different.
It's like whatever it is for the circle graph plus
Plus 1, yep, true. Good, how about over here? This is gonna be 4 are gonna be needed, yeah. How about this? 2, because it's bipartite, right? Regardless of whether n is odd or even. Alright, follow? Alright, good, so that's like fun. Number 11 is actually just like a brilliant problem. We're gonna now turn off this thing and we're gonna go.
No, I skipped that one.
Good. Lights back on, screen up, peachy, make sure we're in frame and stuff. Alright. The dean of a small college wants to increase enrollment in summer school. She has decided to offer classes during 3 time periods: morning, afternoon, and evening. Alright, excellent choice. Students may enroll in 1 or 2 courses. She has found 10 professors who are willing to offer summer courses. The dean has asked students to indicate the courses that they're interested in so that she can decide which courses should be scheduled in the 3 time slots in order to maximize the number of students who will be able to roll into courses should they desire to do so. Okay, get it? Ish?
Ish.
Okay, there's morning, afternoon, and there's evening, and then there are 2 classes. What should we call the class?
Discrete math and Yeah.
Good, let's call class number 1 and class number 2.
Class number 1.
All right, and so here's the idea, right? There's a class number 1 and there's a class number 2. Students might choose to take just class 1, just class 2, both, or neither. Additionally, they're only available, these classes, at certain time slots. So, okay, how can we make a schedule taking everyone's needs into consideration as much as possible? Well, the dean used her survey to produce the following graph. Each vertex represents one of the wait, I think I screwed this problem up. There are 10 courses. There are 10 possible classes on offer, but students can only take 2 of them. Is that correct? 1 or 2. Yeah. Students can only take 1 or 2 classes. So this chart, let's erase this chart because that was just a misunderstanding of the problem. There are 10 courses. All right, and students can take either 1 or 2 courses. All right, so let's check it out. We have this graph. I will now reproduce this graph right here. 1, 2, 10, 8, 4, 1, 3. 2, this is kind of a crazy graph. 1 goes to 6, 6 goes to 9, 9 goes to 7, 7 goes to 4, 5 goes to 8, and 3, and am I missing any? I couldn't have done that right in the first try. 2 goes to 9. 6. 2 goes to 9. And 10 goes to 2 and 8. 8 goes to 5 and 9. And no one's even remotely helping me. Thanks, guys. 5 goes to 6. And 3, good. Good, all right, what the hell is this graph? It is a graph of the 10 courses. There is an edge between 2 courses if at least one student wants to enroll in both courses. Careful with the Polyhedra. All right, so what is the interpretation of this edge between 1 and 2?
At least one
student who wants to take class 1 and class 2. What is the interpretation of the fact that there is no edge between 2 and 6? No student wants to take class 2 and class 6. Therefore, what can I do with class 2 and class 6 if there is no student who wants to take both of them? We can put them in the same time slots. Everyone good now? Same, right. Good, so now this problem becomes, is it possible to schedule the courses so that there are no student time conflicts? If it is possible, do it. Get it? Exactly, Ryan Holland says, aha, I got to the bottom of this crap. I now understand what's going on. Can I get a green? Basically, this becomes, if this is a graph in which adjacency refers to like, they can't be on the same time slot, then if I can color this graph in such a way that no 2 vertices have the same color, if I can do it with just 3 colors, then I simply assign 1 color to the morning, 1 color to the afternoon, 1 color to the evening. So the question becomes, what is chi for this graph? Is it 3?
It better be. Let's just try it.
Okay, good. I like that attitude. Let's just try it. I make this blue, say, and I maybe make this green. I don't know, I'm just like listening. What should I do next? Make 3 blue also. But then 5 can be...
5 has to be green.
Has to be, well, it doesn't have to be.
Oh, no, it doesn't.
But it could be.
Yeah.
8 can be blue. But now I'm seeing
6 has to be a different color.
6 has to be a different
Yeah,
color.
has to be green.
But also Also, the 6, I think 10 needs to be that same color, right? Or no, wait.
Two has to be green.
2 has to be
Oh,
green?
No, it doesn't.
No, it doesn't, never
It
mind.
has to be, but it could be.
It could be green.
But then 10 would have to be red.
Yeah, no, it can't.
Did I win or did I screw up?
Two has to be red.
No,
Yeah,
no,
two can't be green.
Two has to be
Two has to be
red.
red.
2 has to be red?
Yeah,
Because otherwise.
Because of 9.
has to be
and
green.
then not, and then 10 has to be green.
10 has to be green.
Wait,
Yeah.
that still messes stuff up.
Wait, does it?
Nine.
No, it doesn't.
No, it
No,
doesn't.
it
Yeah.
doesn't.
Because
Oh, yeah,
9 can now be
can
green.
9 can be green, 7 can be red.
7 can be, so make 7 blue.
No, I think it can be red or blue, right?
It can, but make it blue.
Okay.
Okay, he wants it blue. Okay, there, it works.
We did it! So by coloring vertices in such a way that no 2 adjacent vertices have the same color, 1, we have established that for this graph chi is 3, 2, we have established that all students can get what they want if we simply make the morning classes red, say afternoon blue and evening green. Get it? Good. Part B of the problem says, is it possible to eliminate the morning session without causing any time conflicts? Just like no, right? Because that's what we have established by showing that you can't do this in 2 colors.
I mean,
Like,
you can eliminate it and then just screw over this.
you can eliminate it and just some people just don't get what they want. Good. Woo! Alright. Let's spend like 3 or 4 more minutes only doing this. Oh, we should do 15 because it's like simple but like worth talking about. This is duality. 15 says, yo, show that the graphs G and H in the following diagram are isomorphic, but their dual graphs are not isomorphic. Whoa. Okay, I think I did this in 5th period, but not 9th, possibly. So here is a graph, and the graph looks like this. I'm not going to bother talking about points. So this is graph G, and next to it, I shall draw a different graph, graph H. Blah, 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 and blah, 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 blah. Okay. Claim by the book these 2 graphs are isomorphic. True? Is that obvious?
Just like drag this far. It's pretty obvious.
Yeah, just put that one
You just
aside.
drag the 2 there out and put the one on the far right in, and then it's all good.
Say it again.
You drag it far right.
Oh, drag this point in?
And then
Yeah.
drag.
And that's
And then
you
are you just done at that point?
All you
Yeah.
have to do is move that one in.
No, literally you just
Yeah.
can put
Literally
this
just
point,
put that
put that point
Yeah,
there, done.
that works.
Okay, good. Alright, so these 2 graphs are isomorphic. So these are 2 different embeddings of the same graph, effectively. Agreed?
Yeah,
Okay,
sure.
but as these are different embeddings, now we're back to like the kind of original problem, which is, can these regions be colored? Well, in order to do that, we basically make the dual. What is the dual of any graph? You put a vertex in the center of every region. Don't forget the outside region.
The dual of that one is going to be bipartite.
I don't know, about to find out. And then you connect 2 vertices if they're, let me put this a little farther away. You connect 2 vertices if and only if their regions share a border. And how many borders? Okay, so let's do the easy ones first. These 2 share a border, 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 these 2 share a border. But there are more borders. In particular, they all share a border with the outside, right?
One
And
that
act-
says 2 borders.
actually like a bunch. What's up?
That's stupid.
That one there.
The one on the far left shows 2 borders of the outside.
That's right.
That's dumb.
And then we get a little bit of and la 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 la. And that it?
Yep.
Yeah.
So I've sort of every edge on the original graph like has like a line to it. Cool, cool. And so there's like a relationship between a graph and its dual. If graph, so if G has like the original G has a certain number of vertices, edges, and regions. And I guess the property here is that the number of regions in G is the number of vertices in the dual.
Yeah.
But I think it's also true in the other direction, right? The number of edges in the G is the number of edges in the dual, right? Yeah. And edges are the same, right? Because for every edge it was an edge. All right, good. All right, well, when I produce the dual of H, I can get like a different graph, I think. That's what the exercise told me was going to happen. So we get a little of this, a little bit of this. So we get a zomp, 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 zomp. And then, oh, I forgot the outside. So we get a la 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 la. And then we get a round and a round.
There's like one in the middle.
Did I miss one?
Between.
I did.
It's a,
Okay, now I think I'm good. Okay, the claim in the exercise was that these two graphs, these two dual graphs, are not isomorphic.
yeah, they're not.
They're not.
Well, how is that
The
clear?
one on
It's
the
not
left is
clear to me.
bipartite and the one on the right is not.
Damn. This is bipartite, is that even true?
I don't think
It is.
I think it is true, because there are no odd cycles. No, there is an odd cycle.
Oh, you can
Oh,
just look
yeah.
at the outside.
Never mind.
It's not obvious to me that these are not.
Well, look at the outside point, then H, that one has 4 edges.
Yeah.
And nothing else.
Oh, boom, there you go. This graph has a vertex of degree 5, and the one on the right simply does not.
Yeah, that's it.
That's pretty good. Alright, good. Alright, that was like duality. Good, there was like one more interesting homework assignment. That was like pretty hard, I guess.
Which one?
Which was 18.
Okay.
18 said, this was pretty lame that I'm just like gonna just tell you guys how to do this because none of you did it. But whatever. 18 says that epsilon is less than 2n minus 4 if G is planar simple connected connected with epsilon edges and vertices, and there's the additional piece of information that every region has at least 4 bounding edges. Every region has at least 4 bounding edges. All right, this sounds like a hard problem, and I guess it is, but it is like the exact problem that we did already. That was number 1 from the homework a couple days ago, which we just straight up did in class. That was maybe like Tuesday or something, or Wednesday. So it's almost the exact same thing. So if you follow does anyone remember the problem I was talking about, which culminated in epsilon is less than like 3n minus 6?
Yeah.
So, all right, so let's walk through the steps. Take every region. What do I know about every region? It's guaranteed to be bounded by at least 4 edges, right?
Yeah.
So what is the minimum degree of a region? 4, right? Yeah. All right, so if the degree of every region is greater than or equal to 4, then what can I say about the sums of the degrees of all the regions? If every region has degree 4 or up, then if I add up the degrees of all the regions,
Depends how many regions.
it's
there are.
greater than or equal to 4 times the number of regions, which is rho. Agreed? Okay, well also, what do I know via handshake about the sum of the degrees of all the regions? It's 2 times the number of edges, because when you count the degrees of every region, you're counting the number of edges that border that region, but then every edge gets counted twice, yeah? Okay, so this is a math fact, that the degree of every region is, the minimum degree of every region, can you stop doing that?
Yep.
Is 4, because that was part of the problem. So since that's true, the sum of the degrees of the regions is greater than or equal to 4 times the number of regions. Also, by handshake, the sum of the degrees of the regions is 2 epsilon. So that tells me that 2 epsilon is greater than or equal to 4 rho, yeah? And therefore, rho is less than or equal to epsilon over 2. This should ring a bell. This is almost the exact logic we went through for that other problem. Now we just throw it all into Euler's identity, which says that the number of vertices minus the number of edges plus the number of regions is 2 if it's simple, planar, and connected. And so what I have is that so solving for rho, I get that rho is like whatever it is, 2 minus n plus epsilon. And rho is less than or equal to epsilon over 2, so 2 minus n plus epsilon is less than or equal to epsilon over 2. All right, doing some like math and stuff. I get that epsilon over 2 is less than or equal to n minus 2. Is that what I was trying to show?
Yeah.
Basically it is, right? That epsilon is less than or equal to 2n minus 4. Good? Alright, good, we have 10 minutes left. Back to Polyhedra. Is this the class where I passed out a packet yesterday?
Yeah.
Does everyone have that packet? Let's finish it, or make some progress on it if we can. Back to the other board. How far did we get in class?
We got up to the last page. The last page was the only thing we didn't do.
Okay, good. Let's jump to the last page then. Boom, go.
Oh, that was this.
Also, this polyhedra is cool. This is like the first one. This is the
So
first.
how could-
Wait, this is honestly the first one that I've looked at and like. I
Mine is
feel like
blown.
it's somewhat the feeling that you feel when you're at the polyhedra. Like the other ones like are cool, but like I look at this one and like this one's really
So
This one's really this one's really
it kind. So the only other one that this is true of is a tetrahedron, right?
every.
Okay, it's a little bit, it's actually controversial. It's like unclear. There's like,
This kind of looks like a tetrahedron.
combinatorically, there are other relationships that might hold for which you gotta be careful. But there are no other known polyhedra which have the property that every edge borders every other edge.
So I was like.
That kind of looks like a tetrahedron.
Okay, good. What is a truncated dodecahedron, first of all? Wait, we're making a video over here. Yes, it is. You really have to stop doing that. Good. This is a truncated dodecahedron. It's just like truncated dodecahedron, man. You take the dodecahedron and you shave off a little corner so it's every vertex looks like a decagon, and a triangle. That's like information that you need to know. And the principle, the kind of method for doing these problems, the spirit of this is that you do know that it's 10, 10, 3, but you don't know anything else. So don't try to like count the vertices by like being smart, which you could do. It wouldn't be that hard. But instead do it like this way. What's the first thing we do? Woo! Find the angular defect. Yeah, so what is the angular defect?
12.
They're saying 12 degrees. I don't know if that's true or not.
Yeah,
60, 60 plus 144 plus 144.
So a decagon is like got some action over there. It's like an exterior angle is 36, right?
Yeah.
So an interior angle is 144. So if I add up 144 and then like times 2 plus an interior angle of a triangle, which is 60, and I subtract all that from 360, I'm left with, he's just telling me what to do. 240 is like 12. Yep. So I have 12 degrees unused at each angle, at each vertex of the truncated dodecahedron. And what we saw yesterday, Descartes' theorem, is that the total angular defect is basically 720 for any polyhedron with Euler characteristic 2, which all these certainly have. Therefore, how many vertices are there?
60.
60, yep. The number of vertices is 60 because it's Archimedean, so every vertex is the same, every vertex is angular equal to 12. Cool? That's like the big picture. But and by the way, okay, so that's good. So V is 60, there are 60 vertices. How do you get the others? Just like do things. Here you have to be slightly careful because it's two of the same thing meaning, right? So it's like, I have to say like, if I add up twice the number of decagons plus the number of, what do you know?
have to be careful. I just did that.
I think you have to be a little bit